Cycle 2, Lesson 4, we're going to carry on talking about solving applications of different types of functions, particularly using Desmos. Today it's about exponential functions. We're going to look at, again, using Desmos. How are we going to do that? So first of all, just a reminder of transformations, because that could come in handy in how we think about things. So when you do transformations of an exponential function, it looks like this. A is right after the equal sign, like always. K and D are both in the exponent. K is in front of x, D is after x inside brackets, and C is back down, not part of the exponent again. So that's how you're going to recognize the different parts. As for using Desmos, just a reminder, we came up with two methods for doing it. Method 1 was where we graph each side of the equation, find the POI, or method 2 was where we bring everything to one side of the equation, graph the related function, and then find the x-intercepts. So we can use either one of those. So let's jump right in. We've got two examples. The first one is about half-life. Half-life is defined as, in my own words anyway, the length of time it takes for some sort of substance to decay from, to half of whatever its original amount is. So here's an equation for half-life. M at t equals p times 1/2 to the exponent t over h. P is the initial, the initial value, and m is the final amount, and then the exponent t over h is going to just give us how many halving periods occur. And then the base, 1/2, is, we're looking at cutting it in half and cutting something in half. So the first example has Karen working in a laboratory that uses radioactive substances, and that's a common half-life type setup, radioactive decay. The laboratory received a shipment of 200 grams of a radioactive radon, and 16 days later, 12.5 grams of the radon remained. What's the half-life of radon? So we just have to plug different things into their appropriate spots. So it started with 200 grams, so that's going to be our P value. P, in the way this is set up, P is our initial value. The initial value is always that number that's out in front of the power, and we multiply it by it. P, that would also be our vertical stretch if we're thinking in terms of graphs, but in terms of just interpreting the equation, the initial amount is what's going to be P. So 200 grams. 16 days later, that's T, so that's going to go into the exponent. That's the amount of time that's elapsed. And M, or M at T if we wish, is going to be what's left after a certain amount of time. Well, didn't mean to write down the amount, I meant to write down M at T, or just M would be fine as well. So if we put things in their appropriate spots, we have 12.5 equals 200 times 0.5. I prefer to write fractions as decimals when we're working with exponential functions. It just seems easier for calculating to me. 16 over h. H stands for half-life in this case. We want to solve it for h. So we can use method 1 or method 2. Let's just use method 1, because why not, and see what we get. So method 1 is where I graph each side of the function as a separate, or each side of the equation as a separate function. So I'll start with the more difficult to remember one, 200 times 0.5 to the exponent 16 over h. And I'm going to replace h with x. So I'm going to use x and y again. 200. I could either use the times button. As you can see, there's a dot there to represent times, or I can use brackets. Desmos understands that. To the exponent, 16 divided by, and again I'm going to use x instead of h. And then for the other side of the equation, it was 12.5, so I'll just have y equals 12.5. So you can see there's the graph of the exponential function there in red. It starts at 0 because it doesn't make sense we can't have a function for a base, not for a base, we can't have a function that goes below 0. If I get negative, in this case, it's going to screw up our graph. So we're starting at 0, we're going upwards. We've got you can see at 12.5, we've got that horizontal line, and we just want to find the point of intersection. That's 4. That means that our answer is 4. So using method 1, h equals 4. For what? For days, because t was in days, so h also has to be in days. So, not hard to do. We put things in the right place. We use our understanding of exponential functions to help us set it up. And it's quick using Desmos. Here's another example, compound interest. You may remember that using compound interest, this is the formula. And A stands for the final amount because we're dealing with money. So the final amount of money, how much something is worth after a certain amount of time. P is the initial amount, sometimes called the principal. I is the interest rate. Let me just zoom in a bit so I can write neater. Interest rate per compounding period. I don't know of any way to say this in less words, so there you go. So, if you have an interest rate of, say, 12% over a year, but you're compounding monthly, because remember, you can have different compounding rate times. Say you compound monthly, so 12 times a year, I would be 1% or 0.01, because we take our yearly annual rate and divide it by the number of compounding periods per year. And finally, we have n, which is our total number of compounding periods. So again, if we compound every month an investment, but we do it for 10 years, 12 times a year times 10 years means that n would be 120, because there'd be 120 times that interest has been calculated. So for this example, the investment is $2,500. That's our initial amount. In fact, let's write it down here off to the side. I prefer to do this for compound interest ones because we have to do a couple calculations. So 2,500, I'll write that there. I has to be calculated 0.0485. So I change that percent to a decimal first of all, but it's semi-annually, which means twice a year. So we're only going to do half of this for each compounding period. Each 6-month period will get half of 0.0485, which is 0.02425 as my I value. And n is what we're actually trying to find, at least in the short term. And this $4,000 is what it's going to grow to, so that's A. So 4,000 equals 2,500 times 1.02425. Notice how I just added the 1 and the I together, since it's an easy thing to do in my head, to the exponent n. Let's use method 2 this time, where we bring everything to one side and graph a single function. So use method 2, or using method 2. Let's just start over here. Using method 2. So that means I'm going to take this 4,000 and move it over to the other side and subtract it. And so I'll do y equals 2,500 times 1.02425 to the n minus 4,000 in Desmos. I'm just going to use brackets again to show my multiplication. Exponent, and I'm going to use x instead of n again, just for Desmos' sake, minus 4,000. Can't see it on the graph, but that's only because we're using large numbers, which didn't show up on our initial scale. And you can see it does have that exponential shape. It's just that you have to zoom out quite a bit to see it. You can see that the horizontal asymptote's been moved down to negative 4,000 by combining it to a single function. Then it rises very steeply. But it should not be 200, it should be 2,500. And so it rises even more steeply. It's still very close to the origin, but what I care about when I do it all as one function is what is the x-intercept. And the x-intercept in this case is 19.62. N equals 19.62. So time is going to be related to n, but it's not going to be the same as n. N is the number of compounding periods, and they occur every 6 months. So if I want to find how much time has gone by, I divide n by 2 in this case, because it's semi-annual, right? Semi-annual, to get the number of years. So half of that is, what, 9.81, I think? Or approximately 10 years. And the reason why I feel like I want to round it to 10 years in this case is because if we're compounding it every 6 months, you can't have 9.81 years as an option. You could have 9 years, 9.5 years, 10 years. At 9.5 years, it's going to be a little under $4,000, but at 10 years, it's going to be worth a little over $4,000. So I think in the spirit of the question, the correct answer would be 10 years.